Let's continue our discussion of the mathematical formalism of quantum mechanics by considering Hermitian operators and the eigenvalue and eigenvector problems that result from their consideration. What we're talking about here is a Hermitian operator in general. So for a Hermitian operator, I'll just write Q with some hat on it. And you can consider just this general operator to be Hermitian if the following condition holds. The inner product of some arbitrary function, arbitrary state in the Hilbert space, F, inner product with the operator acting on some arbitrary state in the Hilbert space, G, is going to be equal to the operator acting on the state F, inner product with the state G. So if this inner product and this inner product are equal to each other for all F and G, then the operator is Hermitian. These sorts of operators show up a lot in quantum mechanics because Hermitian operators are what we are considering if we're talking about observable quantities in quantum mechanics. Now, in terms of eigenvalue problems, the general statement of an eigenvalue problem looks like the operator applied to some general state is equal to some eigenvalue, which I'll write as lowercase q, in the case of the operator uppercase q, multiplied by that state. So applying the operator to the state doesn't really do anything, it only changes the overall scaling factor by some amount q. So these sorts of eigenvalue problems show up in quantum mechanics all over the time, or all over the place. For example, the time-independent Schrödinger equation is such an equation. We have the Hamiltonian operator acting on a state, giving you the energy multiplying the state, h psi equals E psi. Now, solving the eigenvalue problem gives you one of two general kinds of solution. First of all, what we're going to get are going to be eigenstates. Those are going to be our psi's that solve this sort of equation. Generally, we're going to get a lot of them. And we'll get some sort of eigenvalues. Those are going to be the values of Q that result from application of this operator to a particular solution to the eigenvalue problem. And we're going to get many Q's as well. Each solution to this problem, and there will be many, generally has its own distinct value of Q in this sort of expression. And the sets of psi's and the sets of Q's that solve these problems generally come in two discrete classes. We have discrete and we have continuous. The discrete case means that we have some explicit set of, let's say, psi sub n. There are a potentially infinite number of these psi sub n's, but we can write them down in a list. Psi 1, psi 2, psi 3, etc. We're also going to get some set of q sub n's, where q sub n goes with psi sub n. As an example of where this has occurred already that you've seen, talking about the particle in a box, solving the time-independent Schrödinger equation gave us a set of stationary states and the associated energies. For the continuous case, things are a little bit more complicated. For an example of this that you've seen before, consider something like the momentum operator applied to the wave function, giving you the momentum, the value, multiplied by the wave function. This sort of eigenvalue expression came up in our consideration of the free particle. And under those circumstances, we didn't get a real nice set of solutions. We got wave functions that look something like, well, there was some free parameter k. And our wave function as a function of x looked something like a complex exponential. We had e to the I kx minus h bar k squared over 2m t for the time dependence. Probably we were dividing this by root 2 pi, if I remember correctly, to effectively normalize it within the language of the Fourier transform, at least. So there's no way of writing down psi 1, psi 2, psi 3, psi 4. There is only psi k, and k can take on essentially any value. The eigenvalue that we got was, well, in the case of the momentum operator, h bar k. Given the definition of k that we came up with in this consideration of the free particle, we have an infinite set of continuously variable solutions. This k value can be anything, as opposed to indexed by just an integer 1, 2, or 3 sort of setup. Now, the mathematics that results from a discrete spectrum, a discrete set of eigenvalues, versus a continuous spectrum, a continuous set of eigenvalues, are going to be a little bit different. But it's a little easier to understand the discrete case. It's a lot easier to write down mathematical expressions, so let's consider that case first. Most of the results will still hold, and we'll come back to the continuous case later on in lecture. So the first thing that you probably want to know about the eigenvalues that result from these eigenvalue problems is whether or not they can possibly represent observables. And in this case, the eigenvalues of Hermitian operators are real. You can see that by fairly straightforward application of the eigenvalue equation itself, looking at q hat, the operator, applied to some arbitrary wave function psi, giving you the eigenvalue q, multiplied by the wave function psi. You can take the complex conjugate of that expression, and complex conjugating the left-hand side merely converts this into, well, the result of complex conjugating the operator acting on the wave, or acting on the state, which we're writing in our vector notation as angle bracket on the left instead of angle bracket on the right. Complex conjugating the right-hand side of this expression gives you, well, the complex conjugate of the eigenvalue, q star, multiplied by the result of complex conjugating this wave function, or this state, psi. So again, angle bracket on the left. The other ingredient to understanding why the eigenvalues of Hermitian operators are real is the definition of a Hermitian operator, which says that q acting on some state f, inner product with the same state f perhaps, is going to give you the same result as if you take the inner product of the state f itself with the operator acting on the state f on the right. Operator on the left, operator on the right gives you the same result. Now, if I apply this sort of expression over here, and this sort of expression over here, you can see what's going to happen. Applying the operator on the left turns this into q complex conjugate f, inner product with f, and applying this expression on the right turns this part into q, the number, multiplying f. Now a number inside an inner product like this is just going to factor out, so we're left with q, the number, times f, inner product with f. And the inner product of a state with itself is always going to be non-zero. So I can effectively divide both sides of the equation by this, and thereby show that q star is equal to q. Therefore, our eigenvalues of the eigenvalue problem for a Hermitian operator is going to be a real number. Real numbers means that these are potentially feasible representations of observable quantities. So that's a step in the right direction. Now, we talked about a lot of other facets of solutions for the time-independent Schrödinger equation, for example. What about orthogonality and normalization and whatnot? We can talk about those within the language of eigenvectors and eigenvalues, eigenstates of a Hermitian operator. It turns out the eigenstates of a Hermitian operator are orthogonal to each other. Now, that's not a completely rigorous mathematical statement. I'll point out some of the difficulties with it later on. But in the context of orthogonality, we're talking about an inner product of two different states. So suppose I have q hat, and I'll say the state f gives me some eigenvalue qf, multiplying the state. And then I have a distinct state q, let's call it g, gives me the eigenvalue, qg, multiplying the state g. These two eigenvalue problems are solved for the state f and for the state g. So in principle, I know f, I know g, or qf, I know g, I know qg. Now, if you consider the definition of a Hermitian operator in the context of the states f and g, I have f acting on q times g, and that has to be equal to q acting on f, inner product with g. This is our definition of a Hermitian operator. And we know, considering eigenvalues and our eigenvalue problems here, qg, I can write down that. That's just going to give me q sub g times the state g. So this is going to give me qg times the inner product of f and g. And qf on the left, we've talked about how to do that sort of thing on the last slide. This is just the complex conjugate of this sort of thing. So this is going to give me qf, complex conjugated, times the inner product of f and g. Now, this looks a lot like the sort of expression we were talking about before, but in the case of showing that the eigenvalues were purely real, we were working with the state f and itself, not the state f and some other state g. So, we have some potential problems with this expression. If qg and qf are not equal to each other, and f and g, the inner product here, is non-zero, then we have the same expression on both sides, can be divided out. qg is equal to qf, but that's going to cause some problems. The problem that we run into is that we have a failure of our inequality here. And the inequality that fails if I say divide these things out, qg, if qg is different than qf, then I have a contradiction. The contradiction is that f and g don't have non-zero inner product. If f and g has zero inner product, I can't just divide it out because I'm dividing both sides of my equation by zero. So what we can conclude from this expression is that either f g is equal to 0 or qg is equal to qf. And I'll just say qg is equal to qf. Since we've just shown that the eigenvalues are real, qf star is equal to qf. So we've shown that if the eigenvalues are different from each other, then the inner product must be 0. If the eigenvalues are the same, we are not guaranteed that the eigenstates, f and g, will be orthogonal to each other. In the case that qf equals qg, we describe the eigenvalue as degenerate. And we have to go through some extra procedures in order to ensure that we have a well-behaved set of eigenstates. In particular, what we want to do is something called Gram-Schmidt orthogonalization. And aside from having a lot of letters in it, orthogonalization is simply the process of taking these two states, f and g, and converting them into two new states, f prime and g prime, that are constructed as superpositions of f and g, such that they are actually orthogonal. I won't go into the details here, but it has to do essentially with finding the component of the vector f that is not orthogonal to the vector g and subtracting it off of the original vector f, so that I only have the part of f that is orthogonal to g left over when I've computed f prime. So that's a little bit about the eigenfunctions in terms of their orthogonality. The other thing that we needed to be able to compute meaningfully in quantum mechanics is completeness. We needed to represent states, arbitrary states, as superpositions of, for instance, stationary states, solutions to the time-independent Schrödinger equation for, say, the quantum harmonic oscillator. In the language of linear algebra, the mathematical formalism of quantum mechanics, that's an eigenvalue problem with the Hamiltonian operator. And it turns out that we have the same sort of mathematical formalism there. The eigenstates of Hermitian operators are indeed complete. And I can't really say much more here than just give you a definition. In terms of the completeness, we're talking about our eigenvalue problem as before, giving us a spectrum of eigenstates, let's say psi sub n, and the resulting set of eigenvalues. And it turns out that this is indeed a complete basis. Within the language of linear algebra, the set of vectors here spans the complete space that you're working with. And what that means is that any arbitrary state, let me call it f, can be written as a superposition, let's say n equals 1 to infinity here, of some coefficient n multiplying psi n. So I can express any vector in my vector space as a superposition of this set of vectors. It forms a complete basis that spans any desired function that you would be interested in. You can, given the orthogonality of these states, as shown in the last slide, apply Fourier's trick to this sort of expression and determine that this a sub n coefficient is fairly straightforward to calculate. You just multiply from the left by psi sub n, take the inner product with the state that you want to represent. Now, it's important to note that this sort of statement is not on as solid a mathematical footing as the earlier states regarding orthogonality. The completeness is often not easily proven. It is typically going to be something that we assume, and while in the case of consideration of the wave function, we can write down the time-independent Schrödinger equation as a partial differential equation and apply the language of Sturm-Liouville theory and apply the results of Sturm-Liouville theory in particular to show that the results are complete, or that the set of solutions to the time-independent Schrödinger equation forms a complete set of basis functions. The same sorts of results are typically going to apply here. So while we can't always prove it, we are generally going to assume it, certainly at the level of mathematical sophistication of a course like this. So that's about it for the results. One thing I did want to say before we close here is that all of what I've been stating so far are for discrete spectra. So what about continuous spectra? What if instead of getting a discrete set of eigenstates and eigenvalues, I get a continuous set of eigenstates and eigenvalues? The example I gave earlier was a consideration of the momentum operator as an eigenvalue problem. If I have some arbitrary function, apply the momentum operator, and get that same function back, the solutions that we got looked something like e to the I kx minus h bar k squared over 2mt, with eigenvalues that look like h bar k. Now, first problem, this is not normalizable. So within the language of linear algebra, writing down something like, if I call this psi sub k, in the language of linear algebra, writing down something like psi k, what exactly sense does that make? Can I really say this is normalized? Well, if I have two different values of k, let me say, express this in terms of momentum instead. So I'll write this as a psi sub p. If you consider, say, psi p1 inner product with psi p2, what does the orthogonality actually look like? Orthogonality or normalization? Well, if you write this out in the language that we know, that we've been working with so far, that of wave functions, this is going to be the integral from minus infinity to infinity of, well, this sort of expression. First of all, I've got psi sub p1 complex conjugated, so that's going to be e to the minus I k1x minus h bar k1 squared over 2mt multiplied by e to the plus I k2x minus h bar k2 squared over 2mt. This is all going to be integrated dx from minus infinity to infinity. So in the case that p1 equals p2, meaning this is really the same state, then the exponential argument here is the same, but has opposite signs. So I've got e to the plus something times e to the minus something, which is just going to give me 1. I'm going to get the integral of minus infinity from minus infinity to infinity of 1 dx. What now? That's going to be infinity, surely, right? It's not a very meaningful expression, but it's going to give me something very large. Now, what if, let me move this over a little bit to the left, what if I consider p1 not equal to p2 then? Well, in that case, my integral here is going to have some function of x. k1, k2 are going to be different. In the subtraction here that I get if I combine these two things, I'm going to get some function of x. It's going to be like the integral of minus infinity to infinity of e to the I something x. There's going to be other stuff up here as well. But I've got this sort of oscillatory behavior. You can think of this as cosine plus I sine, in other words. Now, as far as formally defining this mathematically, what this limit says, you've got an oscillatory function, you're integrating it all the way to infinity. It's not going to go to infinity, it's going to oscillate, right? And it's going to oscillate about 0. It's going to average out to 0. So in some sense, we can say this sort of goes to 0. And I should really put this in quotes so that I don't make my inner mathematician too angry. We do know, however, from working with these in the past, that these do form a complete basis. These sorts of things can be used to express any arbitrary initial conditions. We talked about that in the context of the free particle when we wrote expressions like that the wave function psi of x, say, can be written as an integral from minus infinity to infinity of dk, some coefficient, phi of k, multiplied by, say, e to the I kx. These sorts of expressions, this is like the inverse Fourier transform of psi sub k. So given some suitable definition of psi sub k, these e to the I kx, these sorts of functions can actually represent pretty much anything that you might want. Now if we substitute in our definition for phi of k back from when we were talking about these sorts of things, it looks like this. It's the integral from minus infinity to infinity dk from before, and our phi of k was itself an integral from minus infinity to infinity. This time it was an integral dx, and it was, let's not leave it as an integral dx because I've got x in this expression as well. Let's use a dummy variable, my usual squiggle, xi. Integral dxi of psi of xi e to the minus I k xi. So this sort of expression, that was our definition of phi sub k. If I multiply this by e to the I kx, continuing my expression over here, you end up with something that makes a certain amount of sense. In particular, I can manipulate this. Let's consider exchanging the order of integration here and manipulating these such that my exponentials multiply together. You can think of this as the integral from minus infinity to infinity dxi first, and then the integral from minus infinity to infinity dk. E to the I, combining these two things together, I'm going to get something like kx minus kxi. And all of this is going to be multiplied by psi of xi. Now, if this whole thing is going to be equal to psi of x, this expression right here should look familiar. What function gives me psi of x when multiplied by psi of a dummy variable and integrated over the dummy variable? This function here, this guy. We have a name for it. It's delta of x minus xi, or xi minus x. So this is sort of delta function. This is what I'm really going to get out of these sorts of normalization conditions. The infinity that it goes to when p1 equals p2 is like the infinity that the delta function goes to when x equals 0, or x minus xi, or x equals xi. The 0 that it goes to is like the 0 of the delta function when its argument is non-zero. So subject to this version of orthonormalization, that if p1 is not equal to p2, you get 0, and if p1 is equal to p2, you get, well, infinity, but infinity in a useful way, such that in the context of integration I can get functions out that as I would expect. You can prove the same sorts of results for an eigenvalue problem with a continuous sort of spectrum. That's about all that I want to say about these sorts of topics. To check your understanding, let's consider the position operator x hat. Is it Hermitian? What is the spectrum like? Is it continuous or discrete? What are the eigenfunctions of x, the operator? And do those eigenfunctions form a complete basis? So think along those lines, and hopefully that will help solidify this notion of the mathematical formalism that we've been working with in the language of in the context, of Hermitian 3, etc. We're also going to get some set of q sub n's, where q sub n goes with psi sub n. As an example of where this has occurred already that you've seen, talking about the particle in a box, solving the time-independent Schrödinger equation gave us a set of stationary states and the associated energies. For the continuous case, things are a little bit more complicated. For an example of this that you've seen before, consider something like the momentum operator applied to the wave function, giving you the momentum, the value, multiplied by the wave function. This sort of eigenvalue expression came up in our consideration of the free particle. And under those circumstances, we didn't get a real nice set of solutions. We got wave functions that look something like, well, there was some free parameter or problems show up in quantum mechanics all over the time, or all over the place. For example, the time-independent Schrödinger equation is such an equation. We have the Hamiltonian operator acting on a state, giving you the energy multiplying the state. H psi equals E psi. Now, solving the eigenvalue problem gives you one of two general kinds of solution. First of all, what we're going to get are going to be eigenstates. Those are going to be our psi's that solve this sort of equation. Generally, we're going to get a lot of them. And we'll get some sort of eigenvalues. Let's continue our discussion of the mathematical formalism of quantum mechanics by considering Hermitian operators and the eigenvalue and eigenvector problems that result from their consideration. What we're talking about here is a Hermitian operator in general. So for a Hermitian operator, I'll just write Q with some hat on it. And you can consider just this general operator to be Hermitian if the following condition holds. The inner product of some arbitrary function, arbitrary state in the Hilbert space, F, inner product with the operator acting on some arbitrary state in the Hilbert space, G, is going to be equal to the operator acting on the state F, inner product with the state G. So if this inner product and this inner product, those are going to be the values of Q that result from application of this operator to a particular solution to the eigenvalue problem. And we're going to get many Q's as well. Each solution to this problem, and there will be many, generally has its own distinct value of Q in this sort of expression. And the sets of psi's and the sets of Q's that solve these problems generally come in two discrete classes. We have discrete and we have continuous. The discrete case means that we have some explicit set of, let's say, psi sub n. There are a potentially infinite number of these psi sub n's, but we can write them down in a list. Psi 1, psi 2, psi product are equal to each other for all f and g. Then the operator is Hermitian. These sorts of operators show up a lot in quantum mechanics because Hermitian operators are what we are considering if we're talking about observable quantities in quantum mechanics. Now, in terms of eigenvalue problems, the general statement of an eigenvalue problem looks like the operator applied to some general state is equal to some eigenvalue, which I'll write as lowercase q, in the case of the operator uppercase q, multiplied by that state. So applying the operator to the state doesn't really do anything, it only changes the overall scaling factor by some amount q. So these sorts of eigenvalue